So finally, in the third section of Young and Friedman's University Physics, Chapter 21, which is on electric charge, electric fields, we finally get to an equation. I know you've been wondering, where's the math, right? We've been doing all this stuff that I already know from elementary school. Give me some math. And so we're going to ease into the math with Coulombs Law. Coulombs Law is named after, surprisingly, Coulomb. Charles Augustin Coulomb, who lived in the 1700s. And he did some experimentation between charges. We talk about kind of point charges. That's kind of, they don't really exist, right? They're theoretical. Any charged body is going to have a body. But he basically experimented. He brought them closer together. He brought them farther apart and kind of measured what happened to the force. Not Star Wars. Trust the Force, Luke. Not that kind of force. Although, who knows? But basically, what happens to the force as you move these charged bodies, Q1, Q2, closer and farther away from each other? What happens? And here is Coulomb's Law. Coulomb's Law states that the magnitude of the electric force between 2 point charges is directly proportional to the product of the charges, that is Q1 times Q2, the magnitude of Q1 times the magnitude of Q2, and inversely proportional to the square of the distance between them. That is, so it's going to get increasingly large, the force, according to the square of the distance between them. Well, let's stop talking words. Let's show me the formula, Ken. So here it is in formula form. The electromagnetic force, where F surprisingly stands for force and E surprisingly stands for electromagnetic force, F sub E, equals K, a constant, not Ken. I wish it was Ken. Somebody name a constant after me. Q1 times Q2, that's charge 1 times the magnitude of charge 1 times the magnitude of charge 2, divided by the square of the distance between them. It's not really a radius, right? Although, anyway, but the square of the distance between them. So basically what he found was that the force was proportional to the first charge, and it was proportional to the second charge, and therefore it was proportional to the two charges multiplied by each other. But it was also inversely proportional, that is, it got smaller or larger in accordance with the square of the distance between them. And so when you have this kind of a situation, as they discovered in the 1700s and I think Newton in the 1600s, that basically when you have this proportional situation, you just need to find a constant. And so you just do experiments until you come up with what K is. And it turns out that K is 9 times 10 to the 9th power Newton meter square per Coulombs square. Coulomb is a very large unit. It's based upon like a meter. And so a Coulomb's a very large charge. We're not going to encounter a Coulomb, most of us, in our life, hopefully. But anyway, so K is 9 times 10 to the 9th power Newton meter square per Coulomb square. By the way, you might remember the Newton's law of universal gravitation. Remember it? The force of gravity equals a constant G times mass 1, the magnitude of mass 1 times the magnitude of mass 2 divided by the square of the distance between them. There's a parallelism here. And so there must be some deeper connection here, it would seem, although I don't think it's been fully discovered. By the way, the electromagnetic force is much bigger in comparison to the gravitational force. We experience the gravitational force as big because we're big people compared to the lowest level of matter. But proportionally, the electromagnetic force is way bigger than the gravitational force. So anyway, very interesting. That might help you remember one or the other or both of these equations. Constant charge 1, charge 2, or mass 1, mass 2, and divided by the square of the distance between them. Now, we could stop there. In fact, if your brain is full, say, may I be excused? But anyway, there is another form of the equation. Don't worry, it's not that bad. The Q1, Q2 part is the same, except we got this absolute value thing going on. The square of the distance is the same, but we have expressed K in what at least at first seems a much more complicated form. Why are you making things complicated, Ken? I didn't do it. It's not my fault. 1 over 4 pi epsilon sabot, or epsilon 0. You know, it sounds like a drink. I'll have some epsilon 0, please. It's not. No, that's not what it is. But it's a constant. So K, basically, if you solve for epsilon sabot, or epsilon sub 0, it turns out to be 8.8 times 10 to the minus 12th power Coulomb square per Newton meter square. Anyway, But who's counting, right? Now you might say, well, why would we do this? Well, this particular format, 1 over 4 pi epsilon sub naught, is going to show up over and over again in other parts of this journey we're on. And so just trust, we're gonna trust Young and Friedman for now, that this is going to help us later on, even though right now it's like, why are you doing this to me? But it'll be helpful when we get further along the electromagnetic path. All right, the last concept that this section talks about is the superposition of forces, which is, anyway, what does that mean? Superposition means is when you stack things on top of each other. So, here's a superposition of books. So what happens when you superpose forces? Well, when multiple forces are involved, the total force of on any other point charge is the vector sum of all the other charges. So I got a bunch of charges around here, and I want to know what is the net, or the total charge. Yeah, let's say net. The net charge of all these other charges on this teeny tiny little charge over here, or vice versa. What's the net force of these charges over here on this point over here? And basically it's the vector sum. And with the vector sum, if you remember a long time ago in the very beginning of Young and Friedman's University Physics, with vector sums, you get some things add. If they're going the same way, they add. If they're going opposite ways, they subtract. And basically you change, you add it all together. You subtract what you're going to subtract. You add what you're going to add. And whatever, if you took so if you're trying to figure out the force on this point right here, you basically take all of these other charges and add and subtract the appropriate directions of them, and you end up with this all adds up to this, as if it was one other point, and that's going to be that superposition of forces. When it all adds up and subtracts out, it's going to tell you what the total force on any other point charge is. And that's the way it is. The superposition of forces. And we're off. We are now knee-deep into electric charge and electric fields. More to come.